Okay. In the moments that we have that are remaining, I want to make a comment about the margin of error. Okay. So, in response to Stacy's question before, I said, well, what's the margin of error? The margin of error is what's after the plus minus part. So for the purpose of, so in the case of the normal distribution, that's z times sigma x bar. But let's unwrap that. That just was, sigma x bar was just sigma over the square root of n. So it's just z times sigma divided by the square root of n. Is the margin of error. And the margin of error, so it's called capital E. Sorry?
It's called what?
E. All right. Well, and if you have a t distribution, how do you find it? It's exactly. It becomes t times s divided by the square root of n. So E is margin of error. Because E stands for error in this case.
Did we ever need to use this formulas, or did it stand for error?
No, I'm about to say something important about it, which is the last thing I'll say today. Okay. So, what's the relationship between the so far we've been talking about the confidence interval. We said it's a lower value and a higher value. Well, what's the effect of the margin of error on the confidence interval? What happens if your error is bigger? What happens to your confidence interval?
No, actually.
What happens to it's a bigger range of values. Because think back to the formula. This part is your margin of error. So if your margin of error is bigger, what are you doing? You're going to subtract a big number and then add a bigger number. So it's going to make your cutoff values at the ends further out. Not bigger or smaller, but just further out. Now, is that good or bad? To have a bigger confidence interval, is that good or bad? That's bad. That's bad.
Wait, I have a bigger confidence now?
Would you rather say that the mean is between 59 and 61, or between 20 and 120? Right. So that's called being precise. You'd rather be more precise. You'd rather have a smaller range.
And then you see what less numbers, right?
Yes. But what's the problem with having a smaller range? Let's look at what happened in the last problem. If I can get them on, I can't get them on the screen at the same time. Okay. All right. Let me drop down. Notice that in the last question, what we did was we said let's find a 98% confidence interval, and then I said let's find a 95% confidence interval. So what happened when I changed the level of confidence? So when the tails get bigger, what else happens? Oh wait, the confidence gets smaller. So you can say, hey, let's make a smaller range of values, and that's good. But then what's bad that happens? You have less confidence. So there's a direct trade-off there. You can have more precision, a smaller interval, but with less confidence. Okay. So is that clear? Okay. But there's one thing we haven't looked at. Sure. To me, the easiest way to see it is to look at the picture. If you want to make the interval smaller, just move the cutoff values in. But when you do that, what happens? It changes your confidence. So for example, in this problem, instead of having 0.98 in the middle, what do we have? You have 0.95 in the middle. So you have a better interval, but you have lower confidence.
So it's when the confidence level rises.
Right. Here's another way to say it. I'm going to say that the mean is 36.8. I have 0% confidence that that's true, but I'm going to be very precise. Right? That's a useless statement because you have 0% confidence. This is more subtle. There's a trade-off between how precise you are and how much confidence you have. But there's one thing we didn't look at. We did not look at, well, let's look in that formula. There's the z, there's the sigma, and there's the n. Changing the confidence is the same as changing the z-score. Does that make sense? Because when you move the n's in, that's the same as making the z value smaller. Okay. So we saw the effect of changing z. Can we change sigma? You can't. Sigma is what it is. You can't change it. So what's left? N. Do we have control over n? Yeah, we can do a bigger study, which is in fact what we were talking about earlier. Okay. So, let's see. All right. I'm going to come back and I'm going to do this problem next time when we have more time, but I do want to show you one thing. Suppose we want to specify what E has to be. In other words, we don't just want to calculate the confidence interval and then say, hey, by the way, what was the margin of error? What we can do is we can say, what if you want E to be a certain value? What if you want to have a certain margin of error? What you're going to have to do is you're going to have to change your n. So we need a way to figure out what does n have to be. Well, we have a formula for what E is. What is the formula for E? Z times sigma divided by the square root of n. Now you can either plug in values and solve it out, or as we've seen, we can just use algebra. And we can say, if the question is what does n have to be, we want an equation that says n equals. So that's what we're going to do, and we're going to do some algebra. So let's do some algebra and find out what n has to be. So from our original formula for E, the first thing is I don't like fractions, so let's cross multiply. That gives E times the square root of n equals z times sigma. Next, I want to get n by itself, so I want to get rid of E, divide by E. Now I want to have just n, so what do I have to do to get rid of the square root? You square it. So there's the formula for E. Excuse me, there's the formula for n. And remember, this answers the question if I say ahead of time what I want E, the margin of error, to be, what do I have to make n? Confidence or yeah, exactly. Right. And because you're given the confidence, you can find z. Okay. So, at the very least, I've equipped you with this formula. So, if it just says, what is n? In the homework, you now know how to answer that question. Just use this formula. Okay.